Okay, so we just showed that when a number is equal to 0, right, the only numerals that it can have are also the digit 0, right? So let's try to use that now to show that, in fact, the numeric representation in base 10 is unique up to leading zeros. So here's how we state that, okay? Here's our theorem. So we have two different numbers here, okay, and that. These are both kind of numerals, and I want to make it kind of clear what they are. So this one is an minus 1, an minus 2, all the way up to a0. Okay, that's what that number looks like. An is the leading digit. Okay, and this one is bm minus 1, bm minus 2, up to b0. And what we say is that these two are equal. Those two numerals represent the same number. Okay, now I'm going to say that n is less than or equal to m. That makes the proof a little simpler because there's only one case. That's really not a significant restriction, because if it turns out that n is bigger, then I'll just swap it, right? And so I have the b's and then the a's. Okay. Of course, the a sub i's and the b sub i's are simply digits between 0 and 9. Okay. I'm going to insist that the leading digit of both, right? So this is the leading digit, a sub n and b sub n, can't be 0. Okay. And if that's the case, right, if I have these two numerals, right, then what must be happening is that n is equal to m, right, and all of the a sub I are equal to all of the corresponding b sub I, right? So it's actually the same numerals, okay? Now how can we prove this? And we're going to use induction, okay? And let's think of the base case. So this is when n is equal to 0, okay? M doesn't have to be 0, okay, but n is 0. Okay, so what I have is that the sum from I is equal to 0 to n of a sub I times 10 to the I, right? Well, that's really just equal to the sum from I equals 0 to 0 of a sub I times 10 to the I, right? And that's just equal to a0, right? Okay, and somehow this is supposed to be equal to the sum from I equals 0 to m of b sub I times 10 to the a sub I, right? That's the hypothesis. Okay, so what does that tell us, right? Well, I can split this up into two parts. This is b0 plus the sum from I equals 1 to m of b sub I times 10 to the I, right? And we saw earlier how we can factor that 10 out. So that is 10 times the sum from I equals 0, okay, to m minus 1 of b sub I plus 1 times 10 to the I, okay, right? So what do we have? Well, these two things are supposed to be equal to each other, right? Now, a naught is less than 10, okay, because it's a digit, right? So how can I make these two things equal? Well, if I look at the right-hand side, it has b naught, which is between 0 and 9 inclusive, right? And then 10 times some kind of a number, a natural number. Well, 10 times a natural number is, 0 or 10 or 20 or 30 and so on. And when we add that to a number that's between 0 and 9, I should get some other numbers between 0 and 9. So what that tells us is that a naught has to be equal to b naught. There's no other way, because if they're not, right, then this will simply add a factor of 10 to that, and it can't set it up so that that ends up equal to a naught, which is a number that's less than 10. Okay, so that must be the case. And the other thing that must be the case is that the sum from I equals 0 to m minus 1 of b sub I plus 1 times 10 to the I must be equal to 0. Okay, but now here's what I'll do. All right, using the theorem that we just proved that said that when a number is equal to 0, rather when a bunch of numerals is equal to 0, then all of those digits must also be 0. Then I can say that all of the b sub I are equal to 0. Okay. Okay, so all of the b sub I are equal to 0. So what that means is that I have a0, which is whatever it is, right, is equal to b0, right, and then all of these are equal to 0, right. So what that means is that they can't be there, right, because what we said was that the leading coefficient wasn't 0. The leading coefficient of this is b sub m, okay, And so all of these terms, right, all of them are equal to 0, which means that they're not there at all, right? Because the leading coefficient is not allowed to be 0, right? And then A naught is equal to B naught, and M has to also be equal to 0, right? Okay, because none of those leading terms can be there. So that's the base case. This is actually a more subtle base case than we're used to, because typically we just get here and go check, right? But in this case, that leading 0 actually makes things a little bit more confusing, because well, you know, we have this sum and it looks like it's a real thing, but actually it's an empty sum. We're adding no numbers, okay? So right here, this is from I equals 0 to m minus 1, which is to minus 1, right? 0 minus 1. So this term doesn't actually exist. That's just there kind of for show. Okay, so let's try the induction case, okay? So the induction step here, okay, it's going to go like this, okay? So what we have is that n is greater than or equal to 1, okay? So let's look at the sum. Oops, that's a terrible sum. Let's look at the sum from I equals 0 to n of a sub I times 10 to the I, okay? And we want this to be equal to the sum from I equals 0 to m of b sub I times 10 to the I, okay? So what I'm going to do is I'm going to go ahead and rewrite this as before. So what I'll have is a0 plus 10 times the sum from I equals 0 to n minus 1 of a sub I plus 1 times 10 to the I. That should be equal to b0 plus 10 times the sum from I equals 0 to m minus 1 of b sub I plus 1 times 10 to the I. Okay, that's the same that we did before. Okay, and so from this, I'm just going to kind of move things around. Okay, so what I can conclude is that a0 minus b0 is equal to 10 times, okay, the sum from I equals 0 to n minus 1 of a sub I plus 1 times 10 to the I minus b0, I'm sorry, minus the sum from I equals 0 to m minus 1 of b sub I plus 1 times 10 to the I. Okay, now I have a naught minus b naught, so I moved the b naught over, I moved this over there, and actually I got a missing sign, so I'll just put it in front right there. Okay. Okay. Now, what do I know? I want to look at the left-hand side first of all. Okay. And how big can the left-hand side get? Well, a naught and b naught are both digits, so they're natural numbers between 0 and 9 inclusive, right? So if I take a natural number between 0 and 9 and I subtract another natural number between 0 and 9, then the biggest that I can make it is 9 minus 0, which is 9. The smallest that I can make it is 0 minus 9, which is minus 9. So what I have is that the left-hand side, okay, is between minus 9 and 9. Okay. Now let's look at the right-hand side. The right-hand side looks like 10 times an integer, okay, which means that the right-hand side is equal to, let's say, 0 or plus or minus 10 or plus or minus 20, plus or minus 30, and so on, right? So somehow the left-hand side is equal to the right-hand side. And as you can see, the only way that's possible, right, is if both of those are equal to 0. So what I have is that a naught minus b naught must be equal to 0, right? Or a naught is equal to b naught, okay? And the sum from I equals 0 to n minus 1 of a sub I plus 1 times 10 to the I must be equal to the sum from I equals 0 to m minus 1 of a sub I plus 1 times, b sub I plus 1 times 10 to the I. And what I have is the induction hypothesis. Okay, so by the induction hypothesis, right, that means that all of the n minus 1 is equal to m minus 1. Okay, all right, and all of the a sub I are equal to all of the b sub I. Okay, so yeah, so it's true for A0 and B0, and it's true for A1, B1, A2, B2, all the way up to A sub n, which is equal to B sub n. So that finishes the proof. Okay, so it's something that somehow we already knew, right? If we use base 10 notation, then yeah, there's actually only one representation for each number. Okay. All right. I just want to end this with one quick statement, and that is that the only reason that it works is because of this, right? You see, the left-hand side could only be between -9 and 9, and the right-hand side goes 0, 10, 20, 30, and so on. Okay. So that's why when we say that we're using base 10, for example, we only get the digits 0 through 9, because if we also got the digits, say, 0 through 20, right, then I couldn't make that argument. Okay, so one of the ways for the left-hand side to be equal to the right-hand side is for the left-hand side to be equal to 10 and the right-hand side to be equal to 10 times 1. And then all of a sudden I don't have unique representation.